I think in the interest of time, we should get started. It is 11 a.m. Central Time, but I would just wanted to say welcome everybody to the NHERI GSC September general meeting. If you are new, welcome. I know we have a couple of new members joining, and if you have any questions, feel free to throw them in chat or unmute yourself. But in general, we're going to go over some updates and then we're going to move into Lisa's presentation. So we'll just go over some announcements. Again, welcome to our new members who joined us this month. If you want to reach out and learn how to be more involved with NHERI GSC, you can reach out to Daniel, who's at the bottom of this presentation, or you can again DM us while this meeting is going on, or email me, Richard, or Robin. And you would see emails from us often. Feel free to respond to those at any time. We also wanted to share a few conference opportunities that are upcoming, and the abstract submission for those are still open, such as the AAG 2025 meeting. We have the ASCE Engineering Mechanics Institute conference, the International Workshop on Structural Health Monitoring, Young Coastal Scientists and Engineering Conference, and then a few others where the abstract deadline has not even been announced yet, but we wanted to put those on your radar. And then also a few conference opportunities where abstract registration is closed, but you can still attend, such as I know a lot of us go to AGU, and there's some other smaller ones here as well, just to keep dates in mind. I'm going to pause if you want to take a screenshot. Let us know if you have any questions there, but in general, we also have leadership nominations open. I know we just went through a round of elections and not all positions were filled. So if you're interested, there are both some executive committee and RSR positions open, and today's the last day to nominate yourself. Please don't be shy. It is totally okay to nominate yourself. We all do. And elections will be held September 24th to the 26th via email. We'll put the link in chat, but here's also the QR code if you want to sign in and nominate yourself right now via phone. It just takes 2 minutes to fill out this form. We also have a GSC DEI workshop coming up. The title for this workshop is Reciprocity in Natural Hazards and Disaster Research. It is the same workshop we designed for the NHERI RU program this summer. So we've already gone through this workshop once, and we were hoping to hold it for GSC members this time. If you stay back after the meeting today, we will also have a facilitator training. If you're interested in facilitating breakout rooms, they're usually small groups in breakout rooms, and we'd just like you to help out like generating discussion and putting in questions in chat and such. And it's a very good opportunity to put on your resume and also to learn more about DEI and reciprocity. If you're not familiar with the topic, that's totally fine, and you can learn more about it as a facilitator. And now I wanted to move into our general meeting. Guest speaker is Dr. Lisa Wang, who is an assistant professor from the Old Dominican University. And Lisa generally studies community resilience in relation to a lot of hazards like tornado and flooding and sea level rise. And I'm going to pass on the floor to her so she can present to us. And then there will be a Q&A question towards the end, but feel free to put questions in the chat as well.
Okay, so right now, do you mind I share my screen?
You can share the screen.
Sure. Let me see whether it works. Can you see my screen right now? Okay, cool. Yeah. Hello, everyone. Thanks for the candid introduction. So I'm Lisa Wang. I'm an assistant professor in the Department of Civil and Environmental Engineering at Old Dominion University. So first, it's my honor to provide today's presentation to all the online researchers, professors, students, and all the friends. First, please allow me to introduce myself. Before joining ODU, I graduated from Colorado State University with my PhD degree and also the postdoctoral fellowship with Professor John Wang. And I also am a licensed California PE with a couple of years industry experience and teaching experience. So my today's presentation is based on my PhD work and postdoc work at CSU. And the title for my today's presentation is Multi-Disciplinary Community Resilience and Reconnaissance Studies Under Tornado Hazards for Decision Making. So first, if you can see the figure at left-hand side show the United States $2022 billion weather and climate disasters. So we can see, tornado is one of the common natural hazards in the United States. And here shows the number of tornadoes in the United States starting from 1995. So we can see overall, we have more than 1,200 tornadoes happens each year. And then if we want to see the number of lives lost and also economic loss, we can see through the years, there's one year really special, and it's 2011. And during this year, we have more than 500 fatalities and also the almost $9.5 billion loss. And one of the huge tornado events contributing to this high number is called 2011 Joplin tornado. And I will introduce more about this tornado. Whenever we have, severe tornado occurs, and we have a lot of, the public information recorded and published by our social media, and they focus on a lot of things such as tornado building hazard or building damage or school reopening or climate change and tornado hazards and how to build back better or something like that. And then let's go back to Joplin tornado, as I mentioned earlier. So in May 22nd, 2011, so we have a EF5 tornado hit the city of Joplin in Missouri and it caused 161 fatalities and more than 1,000 injuries, and which is the costliest single tornado in U.S. history associated with a $2.8 billion loss. So therefore, a lot of researchers choose to use the city of Joplin as their testbed to perform their analysis. So for our built environment, so we include more than 28,000 buildings and the electric power network, including the substations, wooden poles, and the transmission lines and distribution lines. Since we are multidisciplinary, as the title shows, we not only have the built environment, we also have the social economic environment. For example, in the city of Joplin, and we have more than 50,000 population and more than 23,000 housing units. So as you can see this picture, so 2011 Joplin tornado caused a catastrophic component damage. If you can see this picture, such as a roof covering, walls, or structural roof or windows. And also almost affected all of the building sectors. So residential, Walmart, hospital, high school, and nursing home. For example, here we cannot see any nursing home anymore, but only a lot of wheelchairs left on the street. So therefore, the motivation of my work is definitely to improve community resilience under tornado hazards. And if you can see this figure, so it shows a conceptual description of community resilience. So which means we can retrofit our buildings to improve their performance before the hazard, and measure structural response immediately following the hazard, and examine the recovery following the hazard. And I have two parts of my thesis presentation. The first part is about the community resilience. As I mentioned earlier, I graduated from the Colorado State University, and also through my PhD and postdoc, I work in the NSF-funded risk-based community resilience planning center. So please allow me to introduce our center. So the NSF Center is a 10 years program, and the goal is to improve the performance of built environment for natural hazards, but not only for the single building, but at the community level. And also we see the interdependencies between the physical and economic and the social system. And the goal is to develop a computational environment we call the in-core to provide community resilience assessment to provide decision-making. So as I mentioned, we not only have the physical infrastructure, including buildings, electric power, water, transportation, and we also have the economy system and the social science system. So unlike the conventional civil engineering projects focus on the damage over a single building, even the single component like a beam and a column, we mostly want to check the damage loss, the impact of the entire community under natural hazards. And unlike the traditional civil engineering focus on damage, we also have the recovery. So it's a multidisciplinary recovery, and finally to provide decision-making and enhance community resilience. So this picture or this slide shows the entire in-core flowchart. So and then please allow me to briefly introduce this flowchart because almost all of the examples I want to introduce later is related to this entire in-core flowchart. So it starts from here. So we have an initial interdependent community description. We have the built environment, social system, economic system. And then after applying the hazard model and damage model, we have the damage to physical infrastructure. And then considering the relationship or independency between the buildings and lifeless systems such as the power and the water, and then we have the functionality of physical infrastructure. And then we link them to the social science model and the economic model, we can get the direct and indirect economic and social losses. And with the time, we can predict the community recovery. And for each time step, we can record the community resilience matrix from different angles, such as the population stability, economic stability, and physical service stability. And we will see whether we have sufficient quality solution. If not, we will see based on community resilience goals and based on the policy levers or decision combinations or the economic, social, physical infrastructure constraints such as budgets, and we will whether we have some room to do the optimization. And finally, we are going to provide a visualization dashboard to our decision maker. And then I will introduce some of the example I have worked before about this topic. So my first example is about the multidisciplinary disruption assessment. So in this example, we examined the effect of tornado damaging physical infrastructure and the effect on the population local economy. And then we proposed 3 residential building retrofit strategies as alternative to improve community resilience and explore the effects of mitigation strategies on multidisciplinary resilience matrix. And this figure shows the flowchart of this part. And this figure shows how it can link to the entire in-core flowchart I had showed earlier. So for this example, it starts from initial independent community modeling, including physical environment, economic system, and social system. And then after applying the Haider model and the fragility functions, and we can perform the functionality analysis. Our functionality here is due to building damage and or electric power loss. And then link it to a social science model, population dislocation model, and link it to the dynamic computational general equilibrium model, CG model. It's an economic model, and we can predict a series of multidisciplinary resilience matrices. For example, the physical service matrix, we have the percentage of buildings functional due to damage and or electric power, or percentage of buildings accepting electric power, or percentage of residents serve electric power. And for the economic stability matrix, we have the domestic supply, employment, and the household income. And for the population stability matrix, we have a population dislocation, which can be tracked by different household characteristics, such as tenure status, whether this household are owner or renter, and by race, ethnicity, and by household income. And this figure shows our Joplin building built environment with more than 28,000 buildings, as I mentioned earlier. As you can see, we have 19 building archetypes here, including the residential buildings, commercial buildings such as industry and the shopping mall, and also social institutions such as hospitals, schools, etc. And we also have housing unit inventory. As you can see, we have households from 1 person to 7 person, and group quarter and vacant units. So for the Haider model here, excuse me, and we can provide 2 measures of tornado models. First is about the Joplin tornado handcast based on the field investigation following the tornado hazards. And second, an idealized tornado simulation based on the historical reports from the 1970s to 2011. So here, I assume maybe not all of our audience today is wind engineering related researchers. Please allow me to introduce our tornado models. So for tornadoes, we have the scale from EF0 to EF5. So EF5 is strongest and EF0 is weakest. And if you have this tornado, usually the core area is the highest tornado intensity, for example, EF4, and associated with the highest wind speed, and then move out forward, and associated with a lower tornado intensity and a lower wind speed. And our damage model, no matter for the buildings and also electric power, all of them are controlled by the fragility functions. So fragility functions is a probabilistic assessment and can be used to estimate the probability of this building damage exceeding different damage states. And here for each type of building, and we have 4 damage states. So slight, moderate, extensive, complete. And for each damage state, we have a full detailed description. For example, one component for residential building is about the roof covering. And for different damage state, we have different requirements. For example, 2% damage for the slight and 15% damage for the moderate, etc. And then let's move forward to the functionality CG and the population dislocation algorithm. So this figure shows the interdependency between buildings' electric power. So we can see each blue dot here is each substation, and each substation can provide electric power to buildings inside the service area. And this table here shows a simplified Joplin social accounting matrix. So social accounting matrix is the most important matrix inside the CD model. So we can see as this matrix, we have some sub-matrix here. And one of them is called capital payments. So whenever we have natural hazard, absolutely we have building damage, and therefore the capital stock of buildings will be reduced. This is how the damage model can flow into a CG model, and it causes the inequilibrium of the model. And after recalculation and recalibration, and the equilibrium status can be moved from the old status to new status, and then the CG model can be solved. And then we can predict our economic matrix such as demand supply. And here shows our population dislocation algorithm. Basically, it's a logistic regression algorithm and consider the number of people, vacancy, tenure status, and the value loss and minority populations. And finally, we can predict the dislocation probability of each household. And based on this, we also propose a 3 retrofit strategy here, based on the combination of different major structural elements, such as roof covering, roof shading Newton Python, and roof to wall connection type. Here we can see our household can choose whether they want to use asphalt shingles or clay tiles for their roof covering, whether they want to use toenails or hurricane clips for their connections. And here is our retrofit strategy 1, 2, 3 plans. And if running or using different retrofit strategies and run our multi-disciplinary community resilience assessment framework, we can get these results. It's a percentage of buildings within tornado paths functional due to damage. We can see when using retrofit strategy 3, the percentage of building functional can be increased from 3% to 41%. And we can also see the social economic resilience matrix here from the perspective of the entire community. So we can see, as I mentioned, our economic resilience including employment, domestic supply, and household income. And for each one, it can be tracked by different subsectors. For example, for domestic supply, it can be tracked by housing service 1, 2, 3 is housing service HS. It depends on the price of these residential buildings, and the goods trade other depend on the building utility, such as the shopping mall, etc. So we can see if using the retrofit strategy 3, so with the improvement of building performance, so therefore the economic loss will be reduced accordingly. And if we see the population dislocation resilience matrix also from the perspective of the entire computer community, we can see also we using the retrofit strategy 3, the highest level retrofit strategy. And when improving the building performance, and then more residents would prefer staying in the home and not choose to dislocate. And we can see our dislocation can be tracked by different household characteristics, as I mentioned earlier, such as tenure status, whether our household they are owner-occupied or renter-occupied or nursing facility, by race ethnicity, whether our household they are white alone, black alone, any race but Hispanic, and by household income, and by different group of annual household income. And we can also check the social economic resilience matrix from the perspective of an interdependent physical social relationship. For example, we can see the dislocated household remaining in functional buildings or residential household remaining in non-functional buildings. And then we can see their household characteristics. And we can also examine the social economic resilience matrix from the perspective of a social surveys. So for example, this figure shows the Joplin buildings associated with elementary school attendance zones. For example, if we can predict the number of dislocated households, since their family will dislocate and their kids cannot go to school to maintain the continuation, maintain the education, correct? And since right now we have ability to perform the multidisciplinary community resilience assessment, and the second part of my first example is about the multidisciplinary resilience goals deaggregation. So in this part, we develop a multidisciplinary community resilience goals targeted for routine level, design level, stream level of tornado events, and then the aggregate performance targets for individual residential buildings, and then determine the percentage of buildings that should be retrofitted to achieve the community level resilience goals in terms of physical, social, and economic matrix. Still, this part shows the flowchart of this part, and this shows how it can link back to the entire INCORE framework. So it's starting from developing community resilience skills in terms of physical performance and the social economic matrix. For example, we want to develop a goal. We want to keep less than 3% household dislocated after EF3 tornado. And then we develop a preliminary design for individual residential buildings and perform the community resilience assessment and determine the social economic matrix and see whether the performance can meet the objective we set at the beginning. If not, revise design or objective and re-perform the community resilience assessment until the performance can meet the resilience goals we set at the beginning. So this table shows our community resilience goals associated with different tornado hazard, tornado intensity EF2, EF3, EF4. So we can see our resilience goals from different angles, for example, physical surface matrix. And we have the goals of percentage of building remaining functional and due to damage and low electric power, and population stability matrix, percentage of household or population dislocated, and the economic stability matrix, percentage change in employment, domestic supply, and household income. And here we develop 100 generalized random tornado, idealized tornado models here. Here we use EF2 as example and then apply them to the Joplin community. So we can see they have a start point, they have different start point, end point, and different direction, different length. And for each scenario, we randomly retrofit our residential buildings from 0% to 10 to 100% in interval of 10% and perform the community resilience and see the number of residential buildings that should be retrofitted. And our retrofit design here is consistent as before, as I mentioned earlier, based on the combination of different structural elements. For example, this three figure shows how we randomly retrofitted our residential building as an example from 0% to 40% to 80%. And here are our results. And for example, in order to achieve goal A, the household dislocation matrix control the retrofit level, and at least 34.2% residential building need to be retrofitted. And my second example today is about the residential building recovery. So in this example, we develop methodology based on a multi-layer multi-cloud simulation to model a two-stage recovery process for residential buildings. So including the functional downtime due to delays and repairs. And then we quantify the disaster recovery of residential building impacted by pre and post event policies. Still the flowchart of this part and how it linked to the entire in-core flowchart. So for the flowchart, as I mentioned here, we have two-stage recovery, so delays and repair. So our delay including a couple of impeding factors such as the building inspection, which I will introduce later. And our repair model used to estimate the time for the building physically repaired. And then we assemble these two parts based on the multi-layer Monte-Carlo simulation, and we can predict the time needed for any damaged building from any damaged level to fully repaired. As you can see, our delay time here, including a couple of delay time impeding factors, such as building inspection, engineer mobilization, review, redesign, and the time needed for refinancing and contractor mobilization and permitting. They are within different delay phases. And we can see all of them, most of them can link to a building specific conditions, except the financing. Financing, it depends on the funding resource available to all the household at a different level. For example, whether they can claim the homeowner insurance and whether they can apply for the private loan or SBA loans and whether they have to use personal savings. Here, we use household income as a typical social demographic factor to predict their different ability to assess the funding resource. And our repair model here is based on the FEMA P58 and it can be used to estimate the time needed for damaged building to fully repaired. And after assembling these two parts, we can predict the time. For example, we can see when time equal to 1 quarter, 2 quarters, and 6 quarters. And we can see increasing residential building can be fully repaired. So from the red point to green point, that means the community recovery performance probability has been increased. And based on this, we propose a series of policies that can facilitate community recovery process, such as a mandatory building retrofits and relaxed building permits, hire more inspectors, waive bidding rules, and have financing. And finally, we can track the time stamping building recovery strategy impacted by different policy cases. So for this work, we also have the validation use the real world video data. And then we compare the difference between the analytical results and empirical results. So even though you can see our results have some difference here and they're not perfect, that means that may be because both our simulation and also our empirical data has some limitation. For example, in our simulation, we did not consider that people will dislocate, and mostly we assume people will just stay at home to wait for the building repaired. And our video data may also are limited because they are video data, so they cannot record the damage inside buildings. And my next example is about improved school designs and social service stability. So in this example, we propose a different design combination for reinforced masonry high school building for all the primary structural and non-structural component to the entire building for different performance levels. And then we develop fragilities of the entire building and apply them into the community resilience modeling and to estimate the effect of the improved building designs on maintaining school continuity and avoiding dislocation for school children. And again, this is the flowchart of this part and how it can link back to the entire in-course flowchart. As you can see, for each major structural and non-structural component here, windows, walls, and structural roof and roof covering, and we propose 3 different design levels, and including all the details here. And finally, we can develop the fragility functions of the entire building in different levels, and then apply to the community resilience modeling, and to check the impact of functionality of residential school buildings on school children. And my next example is about commercial building recovery. So in this example, we develop resilience resource portfolio such as personal savings, insurance, loans, and the government grants to support the commercial recovery and quantify the financing delay from personal service and READY framework. And then we perform the commercial building recovery assessment and determine the timestamping building recovery and calculating recovery resilience for building clusters. So this is the flowchart of this part and how we link to the entire in-course flowchart. So I mostly just will emphasize or talk more details about the first 2 examples. And then for the other example, I will just briefly mention what we have done. And for this example, our most contribution is we developed the relationship between the damaged states and the funding resource for commercial buildings. And all of the results are based on the personal savings. For example, we assume when building is in slight damage states, only they use the personal savings or business revenue, they can solve the issue. But if they have the moderate damage states, they have to claim the commercial property insurance. And even more serious, such as extensive complete, they have to use, or our business owner need to use all the funding resource they can access to make their building repaired. And here, I developed video here to compare the residential recovery and the commercial building recovery. So both of them I use the 2011 EF5 dropping tornado, and then make a comparison here. So we can see when the time increase, both the residential and the commercial building can be fully repaired. And usually, when time is close to 2 years, and most residential building can be fully repaired, but the commercial building usually lasts longer. And my last example here is about physical social interdependent recovery. So in this example, we develop a methodology examining the interdependent community recovery process across the physical infrastructure and the social system. And then we examine the integrated recovery process of residential buildings and their household or the community impacted by social vulnerabilities. And also this flowchart of this part and how it linked to the entire flowchart, the entire in-course flowchart. So basically, we can predict recovery from 2 modules. One is the residential building recovery, one is household housing recovery. If without any model integration here, we can put it here. So that means we miss the integration part. So that means when the household housing is predicted to get the permanent housing, and whether they have the ability of their original residential buildings, or whether they have the ability of some vacant units in the community they can rent. So after model integration, and here is our upgraded household housing recovery with green bars here. And the second part of today's presentation is about the tornado reconnaissance. So the first part about the community resilience, this part and the tornado reconnaissance. Maybe you can recall in 2021, we have a huge United States Midwest tornado outbreak. In December 10 to 11, 2011, we have a huge tornado hazard. We call it whole state tornado outbreak, and it caused around $3.9 billion loss and reported more than 90 facilities and at least 600 injuries. And from the reports from NWS, we have more than 60 tornadoes confirmed, close to 70, including 2 EF4 and 6 EF3. And the highest EF tornado, including has the 165.7 miles long and 1.13 miles wide, and the highest tornado wind speed of 190 mile per hour. Excuse me. And it hit a couple of hit a couple of states here in the United States, including Kentucky, Arkansas, Illinois, Tennessee, etc. And Mayfield in Kentucky is one of the communities most damaged during the outbreak here. And we firstly used Mayfield to simulate our models. And based on our data sets, we know for the Mayfield in Kentucky, we have almost 5,000 buildings and almost 10,000 population and more than 4,000 housing units. So following the tornado outbreak, and my advisor, Professor Joe Van Link, organized longitudinal reconnaissance studies with the members from different universities and research institute. And this is our study areas. So our wave 1 is in December 2011, so almost immediately following tornado hazards. And then we selected communities. You can see this red line is reported a tornado center line from the NWS. And based on the locations of the communities, considering both of their damage and social demographic factor, and we selected a series of communities for the tornado reconnaissance study. And for the wave 1, we include Mayfield, Johnson Springs, Bremen, Centertown, Hartford in Kentucky, and Monai, Leachville in Arkansas, and Sandburg in Tennessee, and Edwardsville in Illinois. And right now we have 6 waves already, and we only have 1 last wave designed for this December. And for all the following wave, we want to focus on the 6 communities here. So including the Mayfield, Johnson Spring, Bremen in Kentucky, and Monai, Leachville in Arkansas, and Sandburg in Tennessee. And this slide shows our data collection methodology and study timeline. So as I said, so a tornado is occurred in December 10th. Our wave 1 is in the December 22nd. So it's almost just 10 days following the tornado outbreak. And this is our wave 1. And then 3 months after tornado, 6 months, 1 year, 1.5 years, 2 years, and 3 years. So this will be our last tornado reconnaissance studies wave will be designed for this December. And we mostly use the GoPro camera to record our data. We mount our GoPro camera at the top of our car, and then we drop the car along the street and record a 360-degree video data. And for example, this figure in the middle shows our GoPro GPS tracks for the Mayfield in Kentucky. And here is a typical damage photo in downtown Mayfield. So this slide shows a typical, 360 video we can record from our GoPro camera from different angles. So after data collection, absolutely, we need to do the data processing. So here we use a CAPS interface provided by University of Alabama. So this 2 figures shows the CAPS interface. So this figure maybe shows more details. We can see we have 2 layers in total, a blue point layer and a purple point layer. And blue point layer is our original building data size. It's from the NSI, I will introduce later, is from the natural structural inventory. And based on this data size, and also our video data, and this interface can help us to extract an image from the video data and make them associated with each building. And based on the damaged building images, and we organized a group of our undergraduate students to serve as our data tagging group. And then we provide them the professional training, and they can help us to get the data tagging result. So this is the 2 layer, and this is typical damage images can show from this interface. And as I mentioned, and how they can track the data damage states. So as I mentioned earlier, we are using InCore, and we have 19 building archetypes. And for each archetype, and we have the 4 damage states. So the slide, moderate, extensive, complete. So for example, here is for the residential buildings. And we have different components. So roof carving, roof sheathing, and python, window and door, roof to wall connections. And for different DS1 slide, DS2 moderate, DS3 and extensive, and DS4 complete. And for each one, we have different requirements. For example, it's a 2 to 15% roof carving damage, and then 15 to 50, etc. And based on these, we provide a professional training to our undergraduate students to guide their data tagging work. And then after their extensive effort, they provided our data processing results. For example, this is data from the damage resource for different communities: Mayfield, Monai, Litchfield, Sandburg, Bremen, Downson Springs, if in the different color code. So we can see from this damage result, we can see the real tornado model or real tornado occurs or hit the community and how the damage look like. Since we are longitudinal tornado reconnaissance, so we not only have the damage data, we also have the recovery data, and we also track it and show them at the bar. For example, this is all of the data, draft data from 6 waves we have so far. So immediately response to wave 1 and 3 months, 6 months, 1 year, 1.5 year, and 2 years. That's for our Mayfield building recovery. So here, please allow me to introduce 4 different columns. So RS is the recovery state 1, 2, 3. That means RS1, we assume that building has been fully repaired. Now RS2, that means we assume this building is under repair. And RS3, we assume this building has not started to repair. And the TD is tear down. And that means we found a lot of households, they will tear down their buildings directly and maybe keep their property or parcel vacant directly and not choose to repair or reconstruct their building directly. So we can see with the time, so we can see the number of building fully repaired have been increased, and the not started to repair has been decreased for sure. And then we still have a lot of buildings have not started. That's because we have the delay and a lot of impeding factor. Recall that we have a recurrent model I presented before earlier. So we have a couple of delaying factor, building inspection and building permits or something like that. All of them will result in the number of buildings that had not started repair, even though 2 years has passed. So this is our reconnaissance started part. So, and then we also want to make our in-core modeling, because our in-core modeling start from the Joplin testbed, and all of the models want to apply to the Joplin testbed. But now we also want to make all of our, at least most of our in-core modeling to be applied and or make them generalized and can be applied very widely to all the similar size communities, so we can provide risk assessment, community resilience, and to have more decision makers and with a broader social impact. So therefore, for the Mayfield, we also develop our simulation to perform decision making. So this is our Mayfield building data size from NSI I mentioned earlier, from National Structural Inventory. And for this one, we have a lot of information. For example, we have a sensor block, we have footprint areas, and we have the number of story, etc. And then we manually map our building archetypes to our 19 building archetype we had for in-core using the open source data such as Google Earth and Google Maps. And then based on the reported tornado center line, we develop an idealized tornado model and apply, and then we can predict the building damage. We can get the non-functional buildings in different tornado regions. And also we can predict the recovery for sure, because we have the recurrent model. Actually, our community resilience model and also our reconnaissance study, they can support each other. And the reconnaissance studies can capture the damage recovery data and also can facilitate and validate our community resilience work. So last summary of my today's presentation, almost my 2 major directions what I have done at Colorado State University. And the first part is about the multi-disciplinary community resilience assessment. And second part is about tornado reconnaissance studies. And both of them are including a lot of components. And also I work on all types of collaborations from all the coming professors, students, researchers, collaborators, and friends. So the last words I want to see when natural hazards occurs, so human is as important as building for civil engineering to consider in the future. So that's the end of my today's presentation, and I'm happy to have any discussion with you guys. Thank you.
Thank you. Does anyone have any questions? Feel free to unmute or raise your hand or put them in chat. Yeah, go ahead.
Thank you for the extended and detailed presentation, Dr. Wang.
Yeah, thank you.
Yeah, so I just wanted to say one of the last slides that you show, actually I have a couple of questions. So one of the last slides you showed, you said the number of buildings that have been torn down also increased. Yes, is also increasing.
Mhm.
So a year ago, what do you think is the reasons? And if it's going to be teared down, would it not be earlier? Or what do you think? What is the community response that is causing the tear down to be like increasing as the time goes by?
Yes, good question. Thank you for your question. So I assume you want to show this figure and the
Yeah,
right? Yeah. So you can see with the time, yes, the number of building tear down or building torn down has been increased, right?
yeah.
But the thing is, number of building have not started to be repaired has been reduced. So
Okay.
that means during this time, some building had not started to be repaired and switched to this column. So therefore, so you can see at the beginning, they have not started repair, but not all the building will plan to be physical repair to this side. And
Okay.
some of them will go this side. So some household will choose to tear down their building directly. I think there is their decision. For example, is considering, the price of their buildings. And then because after tornado hazard, maybe it's more complicated. See whether their property, whether their land, whether their building can maintain this price. If it maybe not, maybe just they like to keep their, parcel vacant, right? So it is a complicated process. But anyway, it's because of this red column have two directions. Some of them go to this direction for the repair. Some of them go to this direction. So therefore, the blue column, this number is also increased with the time.
Yeah. Also, like regarding this and in response to the housing recovery and retrofitting that you mentioned,
Mhm.
were these also put in within this community, or was it from this different community? And do you think we could have a relationship if like we have retrofitting or good retrofitting, and if the number of houses that were tore down or were repaired would like change? Do we have a relation with that, or those were different projects?
A good question. So it is a complicated process. So right now we do not think about that all of this question as a subjective way. For example, whether they will think to come back, whether they will to go out or something. We will think about a more objective way. For example, based on their reported race, ethnicity, or tenure status, or household income, because
Okay.
all of this information we can get from census data, census
Yeah.
bureau, and will predict the number of people dislocated. So that means they temporarily move out of this town.
Okay.
But we still focus on this town. We will
Yeah.
not consider the relationship of this town and all the other community they may possible to dislocate. We did not include that part. We
Yeah.
just still see this same community and they will dislocate it. And there is in the future with the time increase and with their residential building fully repaired and whether they will come back, the same group, whether they will come back to this community to find a permanent housing. This is our current process. Yeah.
It does seem a very complex and very
Yeah,
interdisciplinary.
that's true. That's why
Very-
we don't want to include it with a human mental subjective thought. Later will be more complicated. Right now
Yeah.
we start from the objective way. Yeah.
Yeah. Thank you. This is
No
amazing.
problem. Yeah,
Hi there. I also had a question.
sure.
So first of all, thank you for the presentation. This has been amazing. I personally don't work on winds, but I work in floods, and I see some of the data sets are similar. So I just wanted to ask more about your building inventory data set. In terms of
Sure.
like, I know you briefly mentioned where you got the data set from,
Uh-huh.
but I just wanted to know, is this freely available to use data set? And then what's the frequency of how frequently do they collect this data set? Is it like how frequently is it updated? Was it done in a single year? Is it done yearly?
Okay, thank you for your questions. So here I propose the two data sets. I can explain both. First is about the dropping data set because we start from the testbed. So this data set we developed by our field investigation. So that means our group signed a field, send a small group to the field to collect the data, some researcher or some postdoc and PhD student they send to this community and to record their building architect, and also combined with the text data. we have a text data set called atom, and combined with these two data sets, and we develop this original building data sets, this is our dropping building data set. But anyway, this is our test bed. So test bed, that means we have this ability to put a lot of resource, time, energy, effort to develop such a reliable data set. But with the time, we want to apply them to all the similar sized communities. So therefore, we thought about propose a second approach. We think maybe it's not that accurate, maybe it's not most reliable, but at least this is the best resource we can access. So it's called the NSI dataset, so National Structural Inventory dataset. You can Google that. So this is the open source dataset. That means you can access and download by state. And for another question, how often they can update this dataset. So this we cannot do anything. So based on my understanding, they will just renew it every other year, but no one can guarantee whether they will just post it and publish, and whether all of this data is most reliable, is accurate, is updated truly at the time period they mentioned. But at least this is the data source, and we compare with some other data source we can get. At least this one is not perfect, but it's the best we can get so far for free.
Oh, okay. Thank you.
No problem.
Does anyone else have any questions?
Yeah, go ahead.
I guess I have a quick question. You mentioned that it was a tornado outbreak.
Mhm.
How common are tornado outbreaks? I don't know if you know that information.
Tornado outbreak is not that common, but tornadoes is very common.
Okay.
Because outbreak is a very huge one, right? So it will just cost the $3.9 billion. If we have that very often, it will be ridiculous, right? But if we see if we see the number of tornadoes, including all the tornadoes. So in the United States from 1995, you can see overall on average, we have more than 1,200 tornadoes occurred every year. But most of them are relatively small tornadoes, because tornadoes, we have 6 scales from EF0 to EF5. So EF5 strongest, EF0 is weakest. So more than 90% of tornadoes are tornadoes less than EF2. That means EF0, EF1, EF2. So very few tornadoes, we don't want them to have a lot, right? So, but very few of them is a very, very huge tornado outbreak. But with the time and with the impact of climate change, so one thing is confirmed. So both the intensity of tornadoes and also the tornado intensity has been increased. So this is for sure. Yeah.
Yeah, I remember, I think, was it a year or two ago? Didn't we have a tornado outbreak? I remember there was many going around.
Yeah.
Throughout Texas and through Oklahoma.
Yeah.
I wonder
So
if there's some statistic to the intensity of, you have so many F1s. Could you make statistical, predictions of how many F5s are going to be based off of that? Just thoughts like that.
yes, we have this data from the published paper. So I remember I read that part before, but I just did not show it in my slides. Yeah, but one thing I confirm is more than 90% is the tornadoes less than EF2. Yeah. Mm-hmm.
Oh, thank you.
No problem.
Any other questions? Yes, I also had a question about how you choose your social science models. Can you talk a little bit more about that process, and also maybe talk about some that you might not have chosen and why?
Okay, so maybe from here, yeah. So here, first, our center has a lot of social scientists at the beginning. So it depends on how we develop this inquiry framework. As you said, the social science, we have a lot of model, why we choose this one. And also, I think it depends on the most important social science resilience matrix we want to explore. This is the most important thing, or which resilience matrix is the most interested to the public expectation and to the, to decision makers, right? So and then after a lot of discussion with them, and we know, okay, most important thing, or at least a very important thing they care about, is the number of people dislocated. And then based on list code, and we see, okay, what kind of a model we have, and we can explore two list matrices. And then we developed a relative or use some existing models our social scientist team developed before. So I think this is the logic. Yeah. Not what we have, for example, we only have this model and then we use this model and then explore the list matrix. So I think it should be the previous procedure as I mentioned. Yeah.
Yeah, thank you.
No problem.
If there are no other questions at this point, we can just thank you, Lisa, for coming to our meeting and giving this wonderful presentation.
Yeah, no problem.